Lab 3, Creating an Orbit by Ved Rao. So the introduction and purpose. Part 1 of this lab is to determine the mass of the black hole by finding the net force acting on the planet. Part 2 of this lab is to determine the speed at which a spaceship is launched where it can go as close as to the black hole but not crash into it or the planet. The purpose of this lab is to determine the mass of the black hole and at what speed a spaceship needs to get to get as close as possible to the black hole without entering or crashing it. So the fundamental physics ideas used are the Newton's law of gravitation, or the Newton's second law, and this is to find the mass of the black hole using this equation. We are provided one of the masses, which is the mass of the planet, and r squared would be the distance between the black hole and the planet, which we are provided, and that's to find the mass of the black hole. And we also need to determine the net force through finding the momentum by using the formula F net equals dp over dt, and this is to find the initial conditions for the speed of the perpendicular and parallel component of the velocity. System and surroundings. Part 1, the surroundings is the black hole and the star was the system. And part 2, the spaceship is the system and the black hole and planet are the surroundings to the spaceship because there are forces from the black hole and planet acting on the spaceship. So here's the code for code and results for part 1 of the lab. So we plug in the gravitational constant, which is g, and we are provided this mass of the star, and we're also provided that delta t is 86400, which is the number of seconds in a day. We first plug in the initial momentum and final momentum and find the change in velocity and the change in momentum, and this would allow us to find the net force. And then we solve for the magnitude, and we can find that the mass of the black hole is the magnitude of the net force times the magnitude of the star's position times the magnitude squared, and that divided by the gravitational constant times the mass of the star, and this is the same equation as the Newton's law of gravitation. And for the mass, I found that the mass was it is 1.937 times e to the power 34. And the code / results of part 2, we plug in the mass that I found, and I basically plugged in all the equations necessary in the code, and I plugged in values to find the path of the spaceship that would be closest to the black hole without crashing, and that was the speeds, the x and y speeds of these values, negative 4.3 e to the 7, negative 3.2 e to the power 6. And possible errors in part 1 could be miscalculation of delta t for number of seconds in a day, or mistype in initializing the mass of the planet. And any error in part 1 would obviously affect the mass of the black hole, which would affect any results in part 2. And any mistypes can also occur in part 2 as well. So the what if and what does it mean questions. The parallel and perpendicular component of the net force results in the same value, but the value is derived from different concepts. F net equals dp over dt is determined through finding the rate of change of the momentum, which will result in the same value for both components. After playing around with the code, I wasn't able to find the correct velocity, but theoretically, the centrifugal force and the force acting on the spaceship from the black hole were equal. The spaceship would enter orbit around the black hole. Thank you.